Hi, everyone. Are you having a wonderful summer? I want you to just enjoy your summer so much. I'm going to keep these videos really short. And then we're just looking at old knowledge that we learned in general chemistry or honors chemistry. So for some of you, that will be a year ago or not even, right? And then for others of you, it will have been over a year since you've seen this. So I'll attach some other videos if you want further clarification. And of course, you can always email me. But I'm excited to start sending you these short videos, just keep you in the loop and start reminding ourselves about some key chemistry information. So the first thing that I want to discuss is some properties of matter. And so we can look at matter qualitatively or quantitatively. So qualitative, think of your senses, smell, touch, taste, hearing, right? But what about observations that we can make that have numbers attached to them? Because once we put a number on that, then it becomes quantitative. So an example would be if we have a pencil and we make qualitative observations, we go, I see that it's yellow, it's got an eraser at the end, it feels soft. But then if we start putting numbers on that, if I put it on a scale, I go, oh, it's 4 grams. Or we measure it with a ruler and we go, oh, I see that it's 10 inches. Then we are supplying a number which would make it a quantitative observation versus a qualitative one. Okay? Now, in addition to qualitative and quantitative, we also have intensive and extensive. Intensive means that whatever it is that we're observing, it's not dependent on the size of the sample. And extensive means that whatever it is we're observing, it does depend on the size of the sample. So for me, the easiest way to think through and remember this is making, in my mind, I imagine like making a sample bigger or smaller. So if we go back to our pencil, if I take our pencil and we take our pencil sharpener and we decrease the size of that pencil, will the color have changed? No, it will still be yellow. So that would be an intensive property because I could change the size of the sample and it didn't change the observation. Another example of intensive would be density. That even though I removed some of the mass, I also removed some of the volume. So the density stayed the same. It doesn't matter what the size of the sample is. A cup of water. If I have a cup of water, I know that that density of that water doesn't change if I pour some of the water out. Extensive means that whatever it is we're observing does change. Mass is a good one for this. Like we put this on the scale, and what did we say? 4 grams. So then we take our pencil sharpener and we get rid of some of this pencil, and then we put it on the scale again, and now it's 2 grams or 3 grams. So the mass changed when the sample size changed. Volume would be another good example of an extensive property. Right? So weight is extensive, volume is extensive, other intensive, we said density, temperature is another good one. So we can't really change anything except for the size of the sample. So we'd keep it in the same situation, right? The same external factors influencing the item. But if this pencil is room temperature and then we get our pencil sharpener and we get rid of some of it and we take the temperature again, it shouldn't have changed if it's still in the same room. Okay, so here's some lists of observations we can make, and I want you to categorize them as qualitative or quantitative, and then intensive or extensive. So hit pause on the video and do that. And then once you've thought through those, hit play and we'll list them out and see how you do. Okay, mass, there's a number put with this, so that would be quantitative. Color, there's not a number, so that'd be qualitative. We want to put quantitative, color, qualitative. Texture, there's not a number, qualitative. Length, there is a number, quantitative. taste, qualitative. Now, you can make arguments for some of these though, like taste. Like we have Scoville scale, right? Of how like spicy something is. So now there's a number associated to taste. So just keep that in mind. It's not even taste like broadly, it's what was that observation. So if it tasted salty, there's not a number associated with that. So it'd be qualitative. Temperature, there's usually numbers. So that'd be quantitative. Volume, we usually have numbers, quantitative. The temperature at which something boils, boiling point, quantitative. Odor, usually qualitative. Physical state, that means solid, liquid, or gas. Like, is it in a solid state or a liquid state? So there's not a number with that one, so it'd be qualitative. Oh. Qualitative. Okay, now let's think about intensive and extensive. The size of the sample. So if I change the size of the sample, the mass will change. So that would make it an extensive property. But if I change the size of the sample, the color doesn't change. So that'd be intensive. Same with the texture. Length would change though, right? If we get rid of some of the sample, like the pencil, then the length is going to change. And so that would make it extensive. Taste and odor, let's talk about those really quick. Those are intensive. We're not talking about the magnitude of the taste or the magnitude of the odor. So the example I like to give is if we have a bouquet of roses and we smell that rosy smell, and then we get rid of some of the flowers, right? So our bouquet is smaller, we change the mass, but it still smells like roses. Maybe not as strongly, but still roses. It's not like we took some of the roses away and then all of a sudden it smelled like lemons. Okay. Temperature doesn't tend to change when you change the size of the sample. Volume does though, so that'd be extensive. Boiling point, the temperature at which it boils. It doesn't matter how much water we have, it always boils at 100 degrees Celsius when we have 1 atmosphere of pressure. And like we were saying before, odor is intensive and physical state is intensive. Even if we make something bigger, smaller, if it was a solid, it stays a solid. If it was a liquid, it stays a liquid. Now, we can change those things, but that would be influencing other factors other than just like the mass or how much of a sample there is. We're going to be using SI units. Units are super important. So please make sure you're comfortable with time being measured, usually in seconds. Length in meters, we often use centimeters as well. So that little prefix there. Mass in grams or kilograms. Grams is probably more common in chemistry just because it's a smaller unit. We're dealing with smaller things. Temperature, you'll get Kelvin and also Celsius. Technically, Kelvin is our SI unit, but there is a direct correlation to Kelvin. Like if you go up 1 degree Kelvin, you go up 1 degree Celsius. And so we often use Celsius in chemistry as well. And then the amount of a substance, a mole, 6.022 times 10 to the 23rd, like this huge number because we're dealing with teeny tiny little atoms. We'll talk more about moles later. We can combine these units. Like we can take base units and we can get an area, which would give, like, if we're using the base unit of meters, it'd be meters squared. Volume would be meters cubed, and this one it was centimeters cubed. Density is mass per volume, so grams per cubic centimeter. Let's go back to this one. Units multiply and divide, but they don't add and subtract. So if I want the area and I'm doing base times by height, then whatever units I had multiplied as well. Same with volume, base times by width times by height, then the units would also multiply. If we are adding together lengths though, we have to have the same unit, or if we subtract, it has to be the same unit. So an example I like to give is if we have 2 meters plus 2 meters plus 2 meters. So numerically, 2 plus 2 plus 2 gives us 6. but our units aren't 3 meters, our units are meters, right? So like some length plus a length gives us that new length. So when you add and subtract, you have to have the same unit that you're adding and subtracting. When you're multiplying and dividing, they don't have to be the same unit, but the units multiply and divide. So here we had 2 meters multiplied by 2 meters. So numerically, we would get 4, but then the units would be meters multiplied by meters, or a meters squared. Here, we're going to have 2 meters multiplied by 2 meters multiplied by 2 meters. So let's start with that part of this. So 2 times 2, 4 times by 2, 8. So we'd have 8 meters cubed, and we'll show kind of the steps here. So we have 8 meters cubed, but then this whole thing, we're going to have to divide by 10 seconds. So what we end up with, so 8 divided by 10, so we get a 0.8. And now our units would be meters cubed divided by seconds. Oh, I forgot to bring it down 1 second. So meters cubed, let's remove the superscript, divided by seconds. Cubic meters per second, divided by seconds. So then our last one here, 10 grams divided by 2 cubic centimeters. So 10 divided by 2 would be 5. And then our units would be grams divided by cubic centimeters, or gram per cubic centimeter. And then there's common prefixes we put, just like meter and centimeters. So here, a centi means 1/100, or times 10 to the negative 2. So just reminding you about these, the ones that I have highlighted there are the ones that you're going to need to know, that they're not going to supply you with that information on the exam. It's just expected that you know what a micro and a nano is, and that we can apply that to any base unit. Okay, the last thing that I want to mention is measurement and significant figures with measurement. And then in our next video, I'll talk about calculations with sig figs. Okay, there's a level of uncertainty in every measurement, and we have to communicate that uncertainty in the amount of significant figures that we communicate, that we write down. It tells us, I can, without looking at the tool that a chemist was using, if I look at their data and I look at the numbers that they have written down, those numbers tell me how precise their instrument was that they were using. So if we have 2 rulers here, the top ruler is less precise than the bottom ruler. And we need to be able to communicate that in any measurement that we take with these instruments. So as precision goes, human capability, what we're capable of, we can reasonably estimate to a tenth between calibration marks, or lines on a ruler or any kind of measurement device. So here, the top ruler gives us calibration marks that are whole numbers, and then we can make one estimate in between. So for this ruler, it would be reasonable for me to measure 9.5, because I can make one estimation in between the 9 and the 10, but it would be unreasonable for me to estimate any kind of measurement that would be like 9.53. Like, I'm not capable of that as a human with that ruler. But the bottom ruler is different because there's more calibration marks here. we have more calibration. So I can estimate in between those teeny tiny lines. So do you see how there is actually a line on this bottom ruler for 9.5? There's a line that represents that. So that's a certain digit. That's not an estimation by me. So it would be reasonable for me to make one estimation past that. So with the bottom ruler, I could record a measurement of 9.53, the one estimation in between the teeny tiny. This has been on the APA exam, just a heads up. Like, even I feel like on the last one, there was a picture of a graduated cylinder and they like zoomed in on a little spot and said, what's this measurement? And you needed to give the right amount of digits depending on how many lines were on the instrument. Okay, so let's practice. So look at this ruler here. I see all these lines, and as a human, I can estimate in between those teeny tiny lines. So if I want to measure this red object up above the ruler, I am certain that I am past the whole number digit 2, and I am certain that I am past the 2.7 line. And now I'm going to estimate, and I estimate that I'm 0.8 of the way to that next line. And so I have a measured value of 2.78 centimeters. The 2.7 is certain because there's actually numbers, there's actually lines on this ruler that represent 2.7, and the estimated value is the 0.08 because I don't actually have a line on this ruler for 2.78. I only have a line on that ruler for 2.7. And so there's one estimation there. Okay, everyone, like before, write down what you think those measurements are, or think through that, hit pause, and then when you're ready, hit play. And let's see how you do. Okay, I'm looking at this first one on the top here, and I see that there is a line right at 1, right? Like there's actually a line that represents 1. And so I need to make an estimation. So let's see. Oh, let's see, I love this example because there's whole number digits here. And then there's also 10th digits available. So that line, because look at the line right before it. The line right before it was 0.9. And so this line isn't just 1, it represents 1.0. That's what we're certain of because that ruler measures to a 10th. And so now I can make an estimate in between because I certainly have not gotten to 1.1. That's the next line. I may just be a fraction of the way past that. I might be 1.02 centimeters. That would be a reasonable measurement. So what we would have to see with your measurement compared to mine, you would have to have 1.0. And then there's an estimate. So you may have said 1.00, or you may have said 1.01, or you may have said 1.03. But the estimated value, that's the one that can differ a little bit. But those certain numbers, those need to be the same. All right, next one. Oh, next one. I have, okay, 2, 2.5, 6, 7. Okay, let's say hypothetically, we felt like this red object that we're measuring, let's say we're looking at it and it looks like it hits right at 2.7. You may have said that it's a little bit more or maybe a little bit less, but let's say that you're looking at it, you're like, I feel like it's right on that line. But remember, there's actually a calibration mark that represents 2.7. And so that's not an estimate. Like we haven't put our estimated digit on that yet. So the estimated digit still needs to be present. There's lines that represent tenths, but there's not lines that represent thousandths. So we need to put an estimation. And if you feel like it's right on that line, you're estimating that it's 0.1 of the way to the next one. I like those examples. They're a little bit harder. Okay, last example. Oh, meniscus, like the water's being pulled up inside the graduated cylinder. So we don't measure from the top of the meniscus, we measure from the bottom. So we see this little curve, it's got to be from on the bottom of the curve there. So it almost, again, kind of looks like we're right on that line. So let's see, what do these lines represent? Because here's 40 and there's 50. So this would be 41, 42, 43. Okay, so we have, it looks like it's right on 43 milliliters, but there's a line that represents that, right? Like there's calibration marks for the ones place. So we need to include an estimated digit. And if we feel like it's right on 43, then we are estimating that it's 0.1 of the way to 44 milliliters. So that'd be 0.010 of the way. Okay, everyone. Well, I have enjoyed being able to talk about chemistry a little bit this summer. And again, watch the video if you need to. If you need a reminder, I'll send you other ones as well. If you're like, oh my goodness, it's been a minute since we talked about those things, then please do not hesitate to reach out. I'd love to help you and answer any questions that you have. And then I'll send you some more of these videos, either, you know, like once a week or every other week, just so you kind of get through and process the material. But anyways, I'm really looking forward to having all of you in class in the fall. I just love AP Chem so much, and we're going to have a lot of fun in class.